All right, hi guys, so my name is Max. I'm one of the BIO005A SIs for Dr. Maduro's 5A class. And so today I'm just gonna finish out some of the questions that we made for you guys on topic 5. So let's go and get right into it. So this first question on the left asks us, which of the following needs a transport protein to kind of move it across the membrane, right? So the first thing I want you guys to think about is the membrane itself. Okay, so I'm gonna draw this rectangle right here. Okay, and so think about the proportions that we have for everything. So the phospholipid heads, relatively compared to like their tails, right, are kind of small. So I'm going to draw it in like this. With these smaller rectangles, they're going to be the phospholipid heads. And I'm going to write those in as just H for the heads. Okay, and this middle part, you can divide it into two. I'm not going to just because it might get a bit confusing. But that whole inside part, these are the tails, right? So you have the tails going down from one side and the tails going up from the other side. Okay, and so next we got to think about kind of the environments that they interact with. So if this is the outside of the cell, outside of cell, and let's say this is the inside of the cell. Okay, so remember that the heads, they are themselves hydrophilic. Okay, and that means they're also polar. So let's just throw that up there. So they're hydrophilic, they're polar. Same goes for the inside of the cell, right? So we're gonna have hydrophilic and polar heads. On the inside, remember that these tails, they're mostly hydrocarbons, and that makes them hydrophobic or nonpolar. Okay, so now let's go ahead and go back to the question. So the next thing it asks us is a protein carrier. So what are these? These are typically something like an integral protein, something like a channel to let molecules in. The next thing we need to know are what types of molecules are able to pass through, right? So what molecules can diffuse through the membrane? Okay, so for one, we know that small polar molecules can pass, right? Just because they're tiny. So the polar molecules are able to get through the heads, but the tails not so much. But since they're small, they're able to do so, okay? And then two, we also have hydrophobic molecules. That's because I kind of wanted to point out that the membrane is a large part of it is hydrophobic. And so if you're able to get through that hydrophilic part, which again, ratio-wise, as a proportion of the larger hydrophobic part, it's very small, right? So that's the reason why hydrophobic molecules are able to diffuse through on their own. So next, let's go ahead and label each of these molecules, right? So water, this is small and polar, right? So this, for one, is going to need it, right? So this is a polar molecule. But remember that water is very polar to the point where it doesn't really diffuse through, okay? Next is glucose. Glucose, as you guys remember, it's a large molecule, and it's also considered polar. So a large molecule typically can't just pass through the membrane. Remember how it's pretty tightly packed. This is polar and large, so this will also need something to pass through. So sodium ions, not so much. These are, the ions react very harshly with the hydrophobic part of the molecule, and so these will definitely need a protein. So these are, I'm gonna say ions charged, and so these will definitely need a transport protein. Then we have amino acids. So amino acids, remember that they have an amine group and they have a carboxyl group, and those two are very polar. So this is also a polar molecule. And then the R group can also add to that polarity, or it can add non-polarness. And so all of these molecules fall into this category of they're large or they're too polar. And with that being said, all of them will need a protein carrier. All right, so let's go to this next one. So let's compare and contrast phagocytosis, pinocytosis, and receptor-mediated endocytosis. So I'm just going to put like buzzwords on here. And if you want to add more things, please feel free to go ahead and do that. So all of them have something to do with engulfing things, right? Engulfing. So some kind of nutrient acquisition. That's way too long. So I'm just going to put, and it's going to look like NA, but nutrient acquisition. So I'm going to put new ac. There we go. So nutrient acquisition, right? Okay, so let's look at phagocytosis first. So what is phagocytosis, right? Dr. Maduro calls this cell eating. So this is literally when some kind of cell will engulf another cell, right? Pinocytosis is a bit different. This is cell drinking. Okay, and so for cell drinking, this is when you take up some kind of liquid molecules, like water, for example, from the outside. Remember how we said it doesn't just diffuse through, so the cell will have to wrap itself around water. And receptor-mediated endocytosis, this one's a bit different. This one requires the receptors or the membrane-bound receptors to, in a way, bind to the molecule that we want to engulf or take in. Okay, so this one's a bit different, and I'm going to try to fit it in here. There we go. Okay, so next, however you want to fill in these other kind of overlapping parts, that's more or less up to you. I would say that between phagocytosis and pinocytosis, I like to think of these as some kind of food related, right? This is more food related. One of them is eating, another one is drinking. Between pinocytosis and receptor-mediated endocytosis, there's not too many similarities, so I'm not sure if I'd put anything there. Except for the fact that, again, these receptors might be, related to water molecules or some kind of liquid. Same goes with phagocytosis and receptor-mediated endocytosis. So I'm just going to leave those blank for now. But again, if you feel you want to add anything there, please feel free to do so. And lastly, I'm going to go over more of a concept than a question. So the next one is we're going to try to determine the number of ions that we form when we dissolve in water, right? So you might have seen this in chem, but let's go through it again. So the reason we know ions will form is because we have ionic bonds, right? So remember, these are with a metal and a non-metal. I have an example down below of magnesium chloride, and we'll get into that later. I would say when we go through this, let's remember let me write down some things to remember. So we have things like the charge of the molecules, and we have the positions on the periodic table. Okay, so let's go ahead and look at this. So magnesium and chloride, this is going to split with magnesium being our metal, chloride being our nonmetal. And so magnesium, remember that on the periodic table, it's a group 2 element. Since it's a group 2 and it's on the left, we're going to have a charge of +2. Okay? So chloride, we know that, well, for one, we know that chlorine is -1 because it's group 7, right? So I know for sure that chlorine is going to dissociate from magnesium because chlorine's the nonmetal, magnesium is the metal, right? Now it's about how many chlorines do we have. It kind of tells you in the equation itself, but it's also good to note that to kind of cancel out this 2 plus, think about we only have -1. So if you want to get to a neutral 0, which is what we have here, right? The charge is 0. You need 2 of these minus charges to cancel out that 2 plus. So we have 2 chlorine molecules. Now for figuring out how many ions that we'll have together, we would have a total of 3 ions. Okay, and so you can do this for any molecule that is that does dissociate in water. Remember that it needs an ionic bond. So anything like a carbon-hydrogen skeleton, those typically won't have ionic bonds, or they don't, and so they won't dissociate in water. All right, if you guys have any other questions, please feel free to ask your SIs, and thank you for watching.